In this video, we're going to go ahead and finish off Chapter 4 with 4.8 Applications and Models. Pretty short chapter, just 3 examples. Hopefully they're not too bad. First one, we have an angle of elevation example. The height of a mountain is 6,000 feet. The distance between its peak and that of an adjacent mountain is 22,000 feet. And we're talking about the distance between the top of one to the top of another, okay? The angle of elevation between the two peaks is 27 degrees. What is the height of the adjacent mountain? So what we're going to do, and I always recommend with these kind of problems, is draw a picture. Okay, so we have this mountain, kind of looks like a triangle. Okay, it's a mountain. And we're talking about the peak of this mountain. So think of it like this point right here. And it's saying the height of this mountain is 6,000 feet. So from here to here is 6,000 feet. Okay. And then they're saying that from this peak to another peak, so think of it like another mountain that's close by. The mountains are not very, these are not very great mountains, but you get it. So this distance right here is 22,000 feet. I put an extra 2, that should be a 0. So 22,000 feet, okay? They want to know the angle of elevation between this point and this point. So you can kind of see the triangle that's being constructed here. Okay, something like this. You have like a right triangle going on right here. And they want to know the angle of elevation. So if you look in your foldable, I'm not going to bring it out, but if you look in your foldable, there is one part that talks about angle of elevations and angle of depression. It's basically always going to be upward. So you're looking for this angle right here. We're going to call it theta. Okay, angle of elevation is theta. And we need to find the height of the adjacent mountain. So what we're looking for is basically this entire piece. Okay, well, we know that at least from here to here is 6,000. So that gives me basically this part. I know that from here to here is 6,000 feet. Okay, oh, I'm sorry, they gave us the angle. What am I saying? This angle is 27 degrees. Making us do more work here. Yeah, so the angle of elevation is 27 degrees. This one right here. Anyway, back to this. So this from here to here is 6,000 feet. So I need to find the remaining piece that is going to be basically this piece right here. So kind of like this part of the triangle. Okay, so to kind of pull this triangle out, just so you can see what's going on here, we have the following. Okay, 27 degrees. And then we have 22,000 right here, feet. And we are looking for this piece right here. So there is our simple little right triangle. Yeah, we have this number over here, but basically that number is just this number. That's part of the height of this second mountain, the adjacent mountain. So when I do get my answer, all I have to do is take this number, add it to this number, and that'll be the total height. So if you want to kind of make this a little bit more formulaic, the total height will be equal to 6,000 feet plus, let's call this x plus x. Okay, so that's what we're looking for. We're looking for x, we can plug it into that. So let's go ahead and use what we know about right triangles. And I'm going to say SOHCAHTOA, yeah, because if you notice, we have an angle, we have we need the opposite side, and we have the hypotenuse. So thinking about my SOHCAHTOA, okay, remember SOHCAHTOA, which one of them uses opposite and hypotenuse? Give you a few seconds. It is sine. Okay, so sine equals opposite of a hypotenuse. So we're just going to go ahead and use that and set this up. Okay, here's how we would do this. Sine of theta is equal to opposite over hypotenuse. So we're going to translate this into this. Sine of 27 degrees, because that's our angle, it's our theta that I forgot to put in the first, is equal to opposite, which we don't know, so x over the hypotenuse over 22,000. And we'll put the feet at the end. Okay, and we're just going to solve for x. So Let's do that by cross multiplying. Put this over 1, cross multiply, and that gives us 22,000 times sine of 27 degrees, okay, is equal to x times 1 is just x. So this is basically what I need to calculate right here. If you are going to be using Desmos, make sure that it is in degree mode because this is 27. If you don't know how to do that, I'm going to show you how to do that right now. And I was actually just messing with that to make sure I know how to I could show you. So here is Desmos, okay? And we're trying to calculate 22,000 sine of 27. So up here somewhere, if you're using the computer, you might have to look for it. But up here in the settings, okay, you can click on this little wrench, wrench looking thing. And it tells you right here, radians or degrees. We want degrees. So there we go. And then we just type it in. So 22,000. For my sine, I'm going to go to functions. And it's right, it's the first one, trig. So sine of 27 degrees. So 27. And there we go, 9987.79. I'm going to just round it to 0.8. So this whole thing is 9987.8 about feet, and that is equal to x. Okay, so if I want the total height, remember the total height is 6,000 plus x, I'm going to have to add this to that. So let's go ahead and do that here. So our height, I'm just going to leave it as height, is going to be 6,000 feet plus this right here, 9987.8 feet. And then we just add that up together, and that's going to give us, let me see, 0.8, 7, 8, 9, 9 and 6 is 15. So it looks like it's going to be 15,987.8 feet. So it's, significantly taller than the first mountain. And that's it. That's the answer for this one. Done. Next example. We have another triangle problem here, and this one has to do with angle of depression, okay? So here we have a plane is 100 feet high and 1,600 feet ground feet from its landing runway. The plane begins to descend in a straight line. Find the angle of descent in degrees of the plane. So anytime you see the word descent or something about going down, you're thinking angle of depression. So you're kind of thinking something like that. Okay, if you're thinking here's the horizontal, you want to be going downward. So let's go ahead and draw a picture just like the other one. We have a plane. So here is our, well, I'm not really good at drawing a plane, but here is our plane. Something like, kind of looks like a shark, but yeah, there's our plane. And it is 100 feet high. So this is 100 feet. Okay. And it's the ground level is 1,600 feet. So the runway is over here somewhere. Okay. And this is 1,600 feet. The plane begins to descend. So it's going to start doing this, right, to get to the runway. This is the run. I don't know what a runway looks like. Maybe kind of like a road or something. And it's starting to descend in a straight line. So it's not going to, this is a straight line. Find the angle of depression, I'm sorry, descent in degrees of the plane. I'm already giving you the answer here. So basically we're looking for theta right here. This is the angle of descent, and it's an angle of depression. So we're going to do the same thing. You can kind of see that there is a triangle here, a right triangle, and we have an angle. We have the opposite side. We also have the adjacent side. So the trigonometric function that uses opposite and adjacent is tangent. Tangent of theta equals opposite over adjacent. Okay, so let's go ahead and just plug these numbers in. We have tangent of theta is equal to opposite, which is 1,600 feet, or just, you can just use the number, that's fine, over adjacent, which is 100 feet. So, the feet kind of go away at that point. How do you solve something like this? Well, I would start off by reducing if you can. So we have tangent of theta is equal to 16 because, well, we can do the work if you want. These are going to divide evenly, so we end up with 16, which gives us tangent of theta equals 16. Okay, now how do you solve for theta? Okay, here is where our inverse functions come into play. You should remember, or at least look in your notes, that the inverse of tangent is arctangent. So we're going to do arctan on both sides, and I'm going to kind of squish it over here because I did not leave enough room for it. But arctan of this one, and what's going to happen is this is going to go away, and I'm left with theta is equal to arctan of 16. Now, if you have a calculator that does this, great. If not, you can also do the other way to write this is going to be tan inverse. So tangent -1 of 16. Please remember that this right here is not equal to 1 over tangent. These are not the same. This is a reciprocal function, and this one is the inverse function. And we are trying to find the inverse because to get rid of the tangent, we have to multiply times the inverse, okay? So we're going to go ahead and do this. I'm going to show you how to do that in Desmos once again. So let me go ahead and clear the one from before. We have our calculator. We're going to go ahead and plug in one of these, depending whichever one it has. Remember to come up here and make sure it is in degrees. It still is in degrees, so we're good. And we're going to go ahead and go to our trig. So functions. And under trig, you can see that they do not have this notation, but they do have this one. So I'm going to use tan of -1, which is right here. Okay, and I just plug it in. 1, oh, that's not a 1. Let me look and see what I'm doing because I can't see. 1, 6, 16. So there we go. So the angle is 86.4, 86.4 degrees. So that is going to be our angle of descent, 86.4 degrees. Actually, let me move this a little bit because it's getting kind of far from here. This represents the angle of descent. And that is it. And if you get something weird here, like 0.0 something, you're probably in radians. So just make sure that you are in the correct measure form, whether it's radians or degrees. Okay. Last example, believe it or not, we're on the last example already. There is a definition that goes with this one. If you don't understand this last problem, don't worry too much about it. This is just another application where we can use some of these functions. Okay, so we have a definition first. On simple harmonic motion, the definition says that a point that moves on a coordinate line is in simple harmonic motion when its distance, represented by d, from the origin at that time, t, is given by the following. D is equal to A, remember A is kind of like our amplitude, sine of WT, or D is equal to A cosine of W. Now I said W, but because it looks like a W, right? It looks like a W, but this is actually omega, which I mean is not too important. I mean, it's just a variable. But this is omega. It should be a little, it's kind of like, I don't know, like a curved looking W. Okay. But anyway, so this is going to be A sine omega t, or you can use double if you want. W doesn't matter. Where a and omega, or w, are real numbers such that omega is positive, so it has to be bigger than 0. The motion has an amplitude, so we know about that. The period is equal to 2 pi divided by that omega, or w. Now this should look a little bit familiar because we're used to saying, well, the period is 2 pi divided by b, so this guy and b are pretty related, okay? So just kind of keep that in mind. And a frequency of omega divided by 2 pi. Okay, so it's kind of like the reciprocal of that. Here is our example. It says, write an equation, okay, for the simple harmonic motion of the ball in the diagram. So I did my best to draw this picture, but you know, if it's not looking good good for you, go ahead and you can look at the example. This is in the book. It's in 4.8, and there's a better picture here. But basically, let me give a little bit of kind of insight into this one. Um, the But when you have an object that vibrates or oscillates or rotates, it is caused by a wave motion. And that's kind of what we're looking at here. So you're thinking, here's this ball kind of like on I guess, a wire, some kind of coil, okay? And if we leave it at rest, so if we don't move it at all, it's considered to be in equilibrium, okay? And that's represented by this first one right here. If we were to take that and kind of pull it down in a vertical line, we would kind of go past that equilibrium point. So you're thinking you're going to go into the negatives, and this would be considered the negative displacement. Okay. If we scrunch it up, but we're going the opposite way, so now we're doing max positive displacement, where it's still going to be 10 centimeters because that is the amplitude after all. But now we're scrunching it up, and it's before our equilibrium point, I should say, before. Okay. So just a little bit of background information. All we're going to find for this is the equation. So if what I just said doesn't make too much sense, like I said, don't worry too much. We are just doing the math part for this, okay? But if you're super interested, by all means, ask me and we can go over this a little bit more in class if you'd like. So let's go ahead and look at this part. It says write an equation for the simple harmonic motion of the ball in this diagram. So the ball is basically this part right here. We're going to be using the sine function. So d is equal to a sine omega or wt. And why are we using sine? Well, because we're displacing vertically, yeah? So we're thinking y-axis, so y is sine. Okay, so we're going to go ahead and do that. We know that the amplitude is 10 because that's given. It's just 10 centimeters. So what we need to find is going to be our omega, okay? So it does tell us that the period is 4 seconds. So what we're going to do is we're going to use that information to find omega. So let's go ahead and put what we know. So we know that A is equal to 10. And we know that our period is equal to 4. So 4 seconds. And up here, we can relate the period with, I guess I should put, P stands for period. We'll just do it like that because it could stand for a bunch of other things, but we'll do it like that. So period equals P equals 4. Okay. Up here, we relate period and omega. So we're going to set this equal to all this. So 4 is equal to 2 pi divided by omega. And we're just going to solve for omega. Okay, so let's go ahead and do that here on the side. 4 equals 2 pi omega. I'm going to do that by cross multiplying because that just seems like the easier way to go here. So that would be W or 4W or 4 omega equals 2 pi. Okay. Divide both sides by 4. And we get that omega is equal to pi over 2. So now we have A, we have omega, and that is basically all that we need, yeah? So our answer using this equation would be D is equal to 10 sine of pi halves t. And that is it. That's as far as I'm going to make you go for something like this, okay? That's all I have for you guys. Pretty short video. Hopefully not too many questions. If you do have any questions, as always, let me know.